One of the topics that we need to review, because we're going to be using sets a lot, is set theory. And the following notations should be familiar set notations that you've seen. What I recommend is taking a moment, pausing the video, and trying to recall what each of these symbols means and how you might represent a number that belongs to such a set. So this first one, this is the integers. And this just consists of all the numbers. We've got 0, and then we've got plus or minus 1, plus or minus 2, etc. N stands for the natural numbers. And another way that you can think of these is it's the set of positive integers. So it does not include 0, and that's a convention. Some people will say the natural numbers include 0, but for our purposes in this class, we will think of them as only the positive integers. Q stands for the rationals. And this is just a set of any number that can be represented in the form a over b, where a and b are both integers, and where b is not 0. So just a reminder with this set builder notation that we're using here, if you look at this colon right here, we want to interpret that as such that. And remember, this symbol means in. So this I, many of you might think it's the complex or the imaginary numbers, but it's actually the irrationals. We're not going to be dealing with complex numbers in this class that aren't real, so we're just going to be sticking with real numbers. Irrationals, one way you can think of it is it's just all the real numbers minus q. So this subtraction symbol means that you are taking everything in the first set and you are throwing out anything in the second set. So for example, you may have seen before something like r minus the number 2. That just means that that's the set of all x in r such that x is not equal to 2. If you see r plus, this is the positive the positive reals. And this is just the set of all x in R such that x is bigger than 0. And the positive reals are not to be confused with the non-negative reals, which is this last symbol. The only difference here is that we are including 0. So this is all x in R such that x is greater than or equal to 0. So one way you could think of this is it's r plus union the number 0. So we're going to be discussing union and intersection in this video here in just a moment. Another common symbol you might see is the punctured reals. This is just the set of all reals with 0 removed. You might hear it referred to as punctured reals. The reason why it gets that name is because if you think about the real numbers as a number line, it's like you put a hole in it right here at 0. And that's your puncture mark right here. Given two sets, A and B, of real numbers, you can combine them or you can intersect them. And if you combine them, that's what's called union. So A union B, when you put the two sets together in a union, it should be the collection of all x that are real, such that x is in A or x is in B. It could be in either one, it could be in both sets. So if you want to think about it as a Venn diagram, it's just going to be anything that lies in either of these circles. And then intersection takes all the values in A and in B that are in common. So it's going to be x in A and x has to be in B. So they must be in both sets. So it's only this region here. Now, some of you may have already been exposed to indexed families of sets, like when you take infinite unions and infinite intersections, and some of you may not have seen that in your proofs class. I'm going to give us a brief overview. So I'm going to take a look at infinite unions and intersections. So for each natural number little n in the natural numbers, let A sub n be a set. I can talk about infinite union, for example, and the way, if I wanted to say A1 union A2 union A3 union, etc., and put them all together like this, another way that you can write this more consolidated is we use a big union symbol, kind of like a giant sigma in a summation. It's the union from n equals 1 to infinity of A sub n. And if you think about what union means in the context of just two sets, remember we're talking about x has to be in A or x is in B in order to be in there. And so I could come down and I could say something similar here. I could say x is in A1 or x is in A2 or x is in A3, but notice there are infinitely many sets, and that is not a very concise way to talk about union. So instead, we want to come up with a different way to say what it means for x to be in the union. So take a moment and think, how might you quantify x? What's another way to say that x is in A1 or x is in A2 or x is in A3? So the way we want to think of this is that x will be in the union provided that x is a real number and x is in at least one of the sets. I'm saying x is in the union provided x is in R, and to be in at least one of the sets, there has to exist an index for your set such that x is in that set. So there exists an n such that x is in A sub n. So then what if I wanted to talk about infinite intersection? So we can list this out as a bunch of intersections with dots, or more concisely, we can say this is a giant intersection of over the A sub n's. And remember what intersection was up here of two sets, it just meant that you had to be in both sets. So if I've got three sets, like A1, A2, and A3, it means that x should be in all three sets. So I'm really making a claim that x is in A1 and x is in A2 and x is in A3 and this just keeps going on forever. But what I'm really asserting is that X is in every set. So the intersection should consist of all my X and R such that X is in every set. And which quantifier am I using now? So before I was using the existential quantifier when talking about union. In this case, I'm using the universal quantifier, my for all quantifier. So the intersection should consist of all X and R such that for all n in the natural numbers, X is in AN. So n here, little n, is just serving the purpose of indexing the set. If you tell me a value of n, say n is 5, that means I'm referring to A5. And so I'm asserting that no matter what index I pick, if I look at the corresponding set, X has to belong to that set in order to be in the intersection. So let's take a look at an example to make sure that we know how to do infinite unions and intersections. So here I'm going to give you two families of sets. So A sub n is the collection of all if I use a natural number to index it. The set is going to be an interval of the form 0 to 1 over n. So if I look at A sub 1, it means let n be 1 and then generate your set. So what I should get is an interval from 0 to 1. If I look at A2, I get an interval from 0 to 1/2. A3 is an interval from 0 to 1/3. And so what we see, if I were to draw a picture of these, my sets are always going to be open over here on 0, and they're going to go as far as 1, and then potentially, so I'll draw up above this. The next set is going to go like that, and then I go to a third. And what I see is that my right endpoint is essentially just sliding to the right. And if I look at, for example, the set A sub 1, A sub 1 is the largest set. It contains all other sets. So in particular, A sub 1 contains A sub 2, which contains A sub 3. Now you might be familiar with this containment symbol, but maybe you've never seen it written backwards like this. We often see it like this. That means A is contained in B. You can also write it backwards, and I could say that B contains A. So when you have something like this, where each successive set in your family is shrinking but inside the previous set, this is called a nested family of sets. Now in this case, A sub 1 is the largest set and it contains all the rest. You could also have a nested family of sets such that A1 is contained in A2, which is contained in A3, so you could be increasing in size. Looking back up here, you can do something similar for B sub n. You can write out what B1 is, B2, B3, and you'll see that the BNs are also nested. So what I recommend doing right now is to pause the video and try to work through computing the union and the intersection, keeping in mind our definitions. We want to think about, if I'm doing the union of all my intervals A sub n, I want to think about which X values do I want to collect all the X values that appear in at least one of the sets. So it may be useful to draw a picture. If you were to put all the sets down on the same number line, you're essentially asking, what have you shaded, by labeling all numbers all at once for all sets on the same line. And then the intersection is, what's the overlap between all of the sets? So take a moment and try to work on that, and then I will present the solution. So let's take a look at the union. I've written out the precise definition of what it means to be in the union. So we're going to be looking at all the x in the reals such that there is an n. In other words, there is a set that x belongs to. And I want to point out what it means for x to be in a sub n, because remember a sub n is an interval. When you say that x is in the set from 0 to 1 over n, what that really means is that x satisfies an inequality. So I want to figure out which real numbers x are such that they satisfy the inequality for at least one value of n. Going back to our picture of what these sets look like, my first set excludes 0, goes up to 1. So this is my set A1. My next set, I'm going to just draw it above like this, goes up to a half, and that's my A sub 2. And then my next set is going to go up to a third. So notice that as I increase the value of n, I'm not picking up any new values. I'm only shrinking my set. And that's because, remember we said these sets are nested. A1 contains A2, which contains A3, which means as I move to the next set in my list, I'm not going to see any new x values that I haven't already seen. So it turns out if I want to collect all x values that appear in at least one set, I can just use the set A sub 1 itself. That is my union. And the reason why we can say this is because A1 contains A2, which contains A3. In particular, it contains every single A sub n. No matter which one we look at, all of the values in A sub n will be inside A sub 1. Now let's take a look at the intersection. So we said this is going to be all the reals such that for all n, x is in A sub n. So what we're really saying here when we write this out, remember we have an interval, so we're claiming that x satisfies the interval inequality for all n. So no matter what value of n I plug in, x has to be sandwiched in between 0 and 1 over n. Now, a common thing coming back up here, notice that the right endpoint is moving. Every time I try to say, every time I shrink my set, I'm going to be excluding some piece. So like when I look from, for example, let's say I'm looking from just this piece right here, from 0 to 1/2, then notice I have excluded all of the values that sit between 1/2 and 1 because I've moved that right endpoint closer to 0. And as I go on to A3, I'm going to exclude all the values that are bigger than a third. And so some people will wonder, well, what does that mean? We're either going to get 0 or maybe it's the empty set. So one of the questions you might ask is, does the intersection equal just the set with the number 0 in it? Well, if you're asking that question, what you're really asking is 0 in every A sub n? Well, if you're going to be in every A sub n, you have to be in it, and certainly have to be in at least one of them, right? So, for example, is 0 in A1? No. Remember what A1 was. It's an open interval. And 0 is not in that open interval. 0 is not in any of the sets, actually. If it's not in any of the sets, it's certainly not in the intersection. It only takes one set. I just have to show you one set that 0 is not in order to prove that it's not in every set. So my answer overall should be no. 0 is not in the intersection. So certainly the intersection can't be equal to the set 0. 0 is not in there. So now what we might claim is that the intersection is actually empty. So a reminder about what this notation means. This is referring to the empty set. It means there's nothing in it. And you should think for a moment, how do you prove that a set is empty? You probably have some experience doing this from your proofs class, and you may have forgotten. But if someone comes in and they say, this bag is empty, well, you could say, I'm going to assume there's something in that bag, and I'm going to show you that something I've assumed is in there isn't actually in there at all. What I'm using here is proof by contradiction. So we will prove this by contradiction. And what that means is I'm going to assume there is an element in the intersection. I'm going to follow that element along, see what that means, that has to be true about that element, and then show that that's not possible. So I'm going to assume that there exists some x that's a real number, such that x is in the intersection of these sets. Now remember what it means to be in the intersection using the definition. That means that x has to be in AN for all n. And really what we're saying is that 0 is less than x, which is less than 1 over n for all n. Let's take a look at a picture. Now, if x is in the intersection, it has to be in A1. And if it's in A1, it's going to have to sit between 0 and 1. So that means I've selected my x that I claim is in all of the sets, and here it is somewhere between 0 and 1. So remember how our right endpoint worked. So here was the right endpoint over here at 1 for a sub 1. And then we moved it over to a half for a sub 2, and then a third, and then a fourth. And notice that eventually the right endpoint is going to have to move past x. So what we need to do is to say that x isn't in the intersection, we need to find a value of n that corresponds to x, such that we can say, you know, you hand me a value of x, I can hand you back the index that tells me the set whose right endpoint has moved to the left of x so that x is excluded. So for example, I might say, this is just an example, this is not the proof, but imagine that I said x is 0.01. And I wanted you to explain why x is x not in the intersection? Well, you would need to tell me a value of n that x doesn't belong to. And the first value of n that it doesn't belong to is 100. X is not in a sub 100. Remember, a sub 100 is the open interval from 0 to 1 over 100. And since it's open and x is the right endpoint of that interval, we don't include it. Now, if I tried to say that I had some other x value, and I said, well, let's go even smaller. Let's go closer to 0. This x, I can say, is not in the intersection. Well, why? Well, this x is not in A1000. So I want to argue in general why no matter what x value you give me that's between 0 and 1, I can always find a large enough value of n such that the set that corresponds to that value of n excludes x. So if I handed you a funky number like 0.005724, you could probably sit there with your calculator and look at 1 divided by 10, 1 divided by 100, 1 divided by 505, and you could keep increasing the value of n until you found the number that was to the left of x. This is called the Archimedean property, and the Archimedean property is something that we will prove. But for now, we just kind of take it for granted. It says that given an x bigger than 0, I'm supposed to be able to get a natural number, I'm going to call it a capital N in the natural numbers, such that when I look at 1 over that natural number, it's going to lie to the left of x. So that's going to be our candidate. This is the argument for why we say we get a contradiction, because we're going to return the index for which x doesn't belong to our set, and because it doesn't belong to that specific set, it certainly isn't in every set. So again, what we're doing here is we're saying I'm picking an x bigger than 0. In particular, x is less than 1, since we also have to be an a sub 1. But there has to be some 1 over n. I have to be able to divide by a large enough number that's just smaller than x. So if I return to my proof here, we assumed that x was in every set, and now we're going to cite the Archimedean property. So by the Archimedean property, there exists an n in the natural numbers such that 0 is less than 1 over n, which is less than x. So what we're able to say here is that x is not a member of a sub capital N. And that means that x is not in the intersection. If it's not in the specific set a sub n, it's not in every set. So here's our contradiction. We began by saying assume x is in the intersection. We've concluded with saying x is not in the intersection. Therefore, what I can say is that the intersection is empty, because no matter what element I try to say is in there, I can argue it's not actually in there. Now let's consider the other family of sets that we have, the B sub n's. So these were intervals. They look really similar, except the right endpoint is 1 plus 1 over n. So for example, B1 is going to be the interval from 0 to 2. B2 is the interval from 0 to 3 halves, etc. And so if I take a look at what we have, we've got 0, we got 1, and we got 2. B1 is going to be this set. B2 is going to go to 3 halves. B3 is going to go to 1 plus, so 4/3 right here. And what we see is that the right endpoint, what we're doing is we're just kind of moving it closer and closer to 1, but it's always staying just to the right of 1. Now, if I want to figure out the union, we're going to be in a really similar situation to the A sub n's, because these are nested intervals, and so B sub 1 actually captures all of the points that appear in at least one of the sets, because you start with B sub 1 and then you only shrink. So if you want to grab all the x's that are in at least one set, they all have to be exactly the x's in B1. So this is, remember, just by definition, it's all of the x and r such that there exists a natural number. such that x is in Bn, and this is just going to be B1. And that's since B1 contains B2, which contains B3, etc. I want to focus our attention on the intersection. Now the intersection is supposed to be the x's that are in every Bn, and one way I can write this is in its inequality form. So I'm trying to say that for all little n in the natural numbers, 0 has to be less than x, which has to be less than 1 plus 1 over n. And if I look at my picture up here, I see that as I increase the size of n, what's going to happen is my right endpoint is going to push closer and closer to 1, always staying just on the other side of 1. So I'm going to be slowly excluding these values in here as I get closer and closer and closer. So you may guess that the endpoints of this interval of the intersection should be 0 and 1, but then we wonder, do we include 1? We know we don't include 0 because 0 isn't even in the first set, B1. But do we include or exclude 1? And what we're really asking is, does 1 satisfy the inequality? So is 0 less than 1, which is less than 1 plus 1 over n, true for all n? Well, let's look. If I let n be 1, I'm asking, is 0 less than 1, which is less than 2? That's true. What if I increase n to 2? I'm asking if 1 is between 0 and 3/2. Well, that's true. And then I'm asking, is 1 between 0 and 4/3? That's true. What we're using here, we actually want to include this. This is true because we're using the fact that 1 over n is always a positive number. We can start with the fact that for all n, 1 over n is bigger than 0. So if I take that inequality and I add 1 to each side, I get that 1 plus 1 over n is strictly bigger than 1. And we know that 1 is certainly bigger than 0. This right here is exactly saying 1 is a member of Bn for all n. So we should include and the reason why is because the answer to our question about whether or not 1 was in the interval for all n was a yes.